Okay, so uh, so we finished up real gas thermodynamics, which was a bit of a crash course in it. There's more detail than that in the advanced thermodynamics class. But now we're going to go over chemical equilibrium. And so I did start that a bit on Friday, and by defining a partial molar property. And that's really just the change of property psi by the addition of moles of species I at constant temperature and pressure. Okay, so psi is any variable, and we just take, in its definition is you just take the derivative of psi, which is the total amount. So if you think in terms of thermodynamics, you had small h, which was per unit mass, or h bar, which was per unit mole. And if you multiply h times the mass, you get the you had cap h, which was the total amount of enthalpy, not per unit mass or mole, but just joules. So then this basically means you just take the derivative of that total property at constant temperature, pressure, and for all moles being in the number of moles of all other species other than I are being held constant. And the most common one that's probably used would be H, is used quite a bit, and G is also one that we will use a lot because the partial molar Gibbs free energy is actually called the chemical potential. And then I ended off showing an example of the partial molar enthalpy for an ideal gas, and it's just H bar. Okay, so now we have now we want to do chemical equilibrium for a real gas. We need to consider the TdS relations for a multi-component system. So if we have a multi-component system, the enthalpy, Gibbs free energies, internal energies, etc., are not only a function of temperature and pressure, or temperature and volume, or whatever makes sense for that variable, but they're also a function of all the number of moles of each species. So now we take the total derivative of this, and we have these extra species terms here. So we have dg is equal to partial g partial t at constant p and constant composition, plus partial g partial p at constant temperature and constant composition. We've already handled these two terms before. Basically, this term here is minus s, and this term here is v. But we have these extra terms here where we basically have the partial molar Gibbs free energy times the change of number of species, and that's summed over all the species. Because if you have 10 different gases, you're going to have the change of basically the number of moles of 10 different species that you need to consider. So we have this expression here, and we compare with the dg relation that we had for a single component system, and we had that dg was equal to minus sdt plus vdp, and you can compare these two, and basically note that basically this here is just the entropy, and this here, and basically this term here is just the volume, and then you see. And then you see that dg is equal to minus sdt plus vdp plus the sum of the partial molar Gibbs free energy, which is this term here that we just defined on the previous slide, times d and I. Okay, and so basically this means that if you have composition to worry about and that composition is changing, all the TdS relations, you need to add this extra term here. And you have very similar terms for the enthalpy and things like that. Okay, now it turns out that there's a property very important for chemical equilibrium called chemical potential. It's also very important for phase equilibrium too. And so the chemical potential for species I is defined as the partial molar Gibbs free energy. So mu I, which is chemical potential, is just the partial molar Gibbs free energy. They are actually one and the same. And you can show using Maxwell's relations, if you extend those to a multi-species system, you can show that the chemical potential is equal to the partial molar Gibbs free energy, which is equal to the derivative of the Helmholtz free energy A over the change of moles of species I, but at constant temperature and volume. It's equal to the change of enthalpy over the change of moles of species I, but you're holding it at constant pressure and entropy. And similar for the change of energy with respect to the number of moles of species I, but you're holding entropy and volume constant. Note that all of these properties here are not partial molar properties, and the reason that they're not partial molar properties is because temperature and pressure are not being held. Okay, so you cannot find the total Helmholtz free energy by just summing up the number of moles times the partial molar, or times the basically times all of these terms here. Okay, and so that's a pretty common mistake. But now notice what this gives us though is these Maxwell's relations here. If you substitute them to, if we did the same thing that we did for the Gibbs free energy, and basically modified that to include the change of moles, and we substitute in the definition of chemical potential, we see that basically this sum here is just the sum of the chemical potential of species I times dni. Now, if we do the same thing for, say, the first TDS relation, the second TDS relation, etc., and use these Maxwell's relations here, we find that all of the major TDS relations, that all of the extra terms are either plus or minus the sum of chemical potential times dni. Okay, which I think is kind of an amazing result. And so and so that's a very and so that is a very that's a very nice result. And so but basically, what does this mean? So let's consider a chemical reaction in a constant pressure and constant enthalpy process. The overall chemical reaction is the same generic one that we've been talking about since day one, where we have the sum of nu I prime mi goes forwards and backwards from the sum of nu I double prime mi. Okay, and now this reaction can go forwards and it can go backwards. And because it is allowed to go backwards, is that it may not, even if you start at the full reactants, it may not go all the way to the full product state. Is that the chemical reaction might stop just naturally by itself somewhere halfway between the reactants and products. And if you try to cheat it and you start the reaction at full products, the chemical reaction can actually go backwards. And so what we will basically what we want to find is where this reaction stops, and that's chemical equilibrium. So first, let's just examine the TDS relations. So if we look at these, and for our example here, we are fixing pressure and enthalpy. So if you look at these TDS relations, one of these is very easy to work with, and the others would be nightmares to work with. So if we look at this expression here, we have TDS is equal to DH minus VDP. Well, we are holding H constant, so that means this term would go to 0, and we're holding P constant, which means basically this term goes to 0. So if you work with this TDS relation, and these are all valid, you can use either one you want. It's just if you hold two variables constant, typically one of them will be easier to work with than the others. And so basically, if you work with the second TDS relation here, two of the terms drop out, and we only have the TDS is equal to minus the sum of the chemical potentials of all the species times dni. Okay, and so that's basically what we, and so that's basically what we have here. So we just sort of we basically substitute that in, and that for anywhere in the reaction, we have ds is equal to minus 1 over t sum of mu y dni. Now, we can start to realize that for the second law of thermodynamics, for any process, there's no extra heat here being applied, as you can see, we know that ds has to be greater than or equal to 0. Okay, it can only go down if we are removing heat from the system, but here we are not, we are holding H constant, so there is no heat being removed from the system. So we can conclude that if this has to be positive, and temperature is a positive quantity, I don't know what a negative temperature means on an absolute sense. It's unphysical. So that means that to make this entire grouping here positive, the sum of mu y d and I has to be less than or equal to 0. Okay. And furthermore, if we want to find the equilibrium point, that's the point where the chemical reaction stops changing. Well, what does the chemical reaction the chemical reaction stops moving? If the chemical reaction stops moving, that basically means that the chemical composition is no longer changing, or DNI for all species is equal to 0. Okay, so if we look at this criterion here, that the sum of mu y DNI is less than or equal to 0, we can, if all the DNIs are equal to 0, the sum of mu y DNI at chemical equilibrium, that is where the chemical composition is no longer changing, is equal to 0 at the chemical equilibrium point. So this basically means that this expression here can be used directly to find the chemical equilibrium by maximizing the entropy of the system. So if I plot that, so for a constant a pNH process, we can plot the entropy as a function of the reaction progress, and we'll be dealing with a variable epsilon called the reaction progress variable. It's just a variable. It is dimensionless. It is 0 if you are in the pure reactant state, and it is 1 if you are in the pure product state. So if we were to plot the entropy as a function of this reaction progress, we know that if the reaction progresses, it will go up and up and up and up and up, and eventually we will hit some sort of we will basically hit a maxima. And because thermodynamically we cannot spontaneously decrease the entropy, the chemical reaction stops here, and it stops here at the peak. And so this here, let's say epsilon is equal to 0.4. That would be where the chemical reaction stops. So that means the final mixture would be, say, 40% reactants and 50%, and say 60% products. So it would stop right there. So what happens if you try to cheat the system and you start with, say, pure products? Well, again, the chemical reaction will proceed spontaneously if you are increasing the entropy. So the chemical reaction will basically start here, and then it will go backwards. Because again, you are allowed to increase the entropy, and it will go backwards and backwards and backwards until it gets to the peak, and then it can't proceed to the left anymore because that would require you to spontaneously decrease the entropy. So even if you start at pure products, the chemical reaction runs backwards until you hit the same equilibrium point. Okay, and so basically, if P and H are held constant, the entropy for the system is maximized, and that maxima is the chemical equilibrium point. Okay, are there any questions? Okay, so because at chemical equilibrium, the change of the moles of each species is equal to 0, the general condition for chemical equilibrium, regardless of which variables are being held constant or other thermodynamic constraints that are being applied to your system, the sum of mu I d and I is equal to 0. Okay, this is the general condition for chemical chemical equilibrium, And from the second law of thermodynamics, we also concluded that the sum of mu I d and I is a negative quantity, or is less than or equal to 0. And it is equal to 0 if you are at equilibrium and the reaction proceeds, as long as the sum of mu I d and I is less than 0. Okay, and again, these are this here is a consequence of the second law. Okay, and as I said before, that for a constant H and P process, the chemical equilibrium point can be found by just maximizing the entropy for the system. And if you start at the equilibrium point, moving off of that point would require spontaneously decreasing the entropy, which is of course impossible. Okay, so that was for a constant H and P process. What if we fix two other variables? What if we have say T and P or E and V or T and V? Again, the general criterion is that the sum of mu I d and I is equal to 0. That can be applied to any process. And the chemical reaction proceeds as long as the sum is negative. Okay? So that holds for any process. So now what about other processes? So in general, if you applied those criterion, you can go back to the TDS relations and you can look at, well, which variables are being fixed. So if you have a fixed vessel, it is well insulated. You will be fixing the internal energy, and you'll be fixing the volume. So that means since you're fixing the internal, since dE would be constant and dV would be constant, that means these two terms would go away, and the first TDS relation would be the one that'd be easiest to use. And for a constant energy and volume system, again, if you basically look at this, we know that the equilibrium point is where the sum of the chemical potentials times the change of moles of each species is equal to 0. And that's a negative quantity. So that means if you have a fixed vessel that's at fixed volume and it's well insulated, that means we again maximize the entropy. Now, say we have a constant pressure and constant temperature system. Well, here, this term goes away, but we don't know what to do, but we don't know what dH is, and we don't know what ds is. So this is not a good one to use. So if we fix the pressure and temperature, well, we know dP is equal to 0, so this term would go away for the dG version. And we know that dt is equal to 0, so this term goes bye-bye. So if you fix the pressure and temperature, the Gibbs free energy version of the TDS relations would actually be the one to use. But now notice here that the sign in front of the chemical potential term is actually the opposite of the TDS relations. So this means that at the equilibrium point, where again, this sum is 0, and this sum is always negative, this means that the Gibbs free energy is negative. Or that the Gibbs free energy, I'm sorry, is minimized at the equilibrium point. And you can play this game for any other number of quantities that are being held constant. Okay, so basically, what about other processes? You basically examine the other TDS relations and find the one that makes sense for you based on what is being fixed. So at constant T and P, as I said earlier, you would use you would be advisable to use the Gibbs free energy version. So we have dG is equal to the sum of mu I d and I. This term here is less than or equal to 0, which means that since this is negative, the Gibbs free energy, the change of Gibbs free energy as the reaction proceeds is negative, which means and dG is equal to 0 at the equilibrium point, which means that chemical equilibrium for these fixed thermodynamic variables is the Gibbs free energy is minimized. So a plot of G versus the sort of reaction progress variable would look something like this, and the minimum point here would be the equilibrium point. Now, you may be wondering, well, why isn't entropy maximized for this choice of variables? A, because you are fixing the temperature, you are adding heat to the system. And so if you are adding heat to the system or you're removing heat from the system, the change of entropy is allowed to be negative. Okay, and so it's because for this system here to basically keep the temperature constant, you are adding or removing heat from the system. It is no longer well insulated, and so you cannot rely on maximizing the entropy. Okay, so are there any questions with this? Okay, so now how do we actually go about doing this classically? If you were to take a standard course in combustion, we would spend quite a bit of time discussing what's called a Van't Hoff equilibrium box. And so this is just a hypothetical construction where we have a vessel, there's a giant constant temperature bath, and we have a constant pressure reactor. So we have some reactants A and B coming in tubes. There could be A, B, C, D, E, F, G, and we have some products coming out. And this this constant pressure reactor is large enough that it is that basically it can reach full chemical equilibrium after the products leave our box. Okay, and so for our general reaction, we know that the chemical equilibrium condition is the sum of mu I dni is equal to 0. And applying this equilibrium condition, we are fixing T and P. So that means we would use the DG version of it. That means that the Gibbs free energy, or the change of Gibbs free energy, is 0. And again, alternatively, you can also minimize G. And I'll get into, for when you deal with real gases, I find it easier to minimize the variable and not do it the way that that is done in a lot of combustion books. Okay, and so working with DG is equal to 0, and the partial molar Gibbs free energy is equal to the chemical potential. You can show that that the criterion that the sum of mu I dni is equal to 0 is equal to the sum of G bar dni is equal to 0. This is just by a direct substitution. And if you want to minimize G, G is defined as just the sum of the number of moles of species I times the partial molar Gibbs free energy. Okay. So now we will basically work with this. For our constant temperature and pressure process, so back to the overall chemical reaction given by this. So now we want to find, oops, wrong way. We want to apply this condition here, but we first need to find DNIs for basically all of these reactions. Or I mean, for all of these species. Okay, and so for our overall reaction, we need to find DNI. So again, let's define a reaction progress variable epsilon. I already introduced that, but just to refresh, if epsilon is equal to 0, we have pure reactants. If epsilon is equal to 1, we have pure products. And if epsilon is equal to 0.5, we have a 50-50 mix by mole of products and the reactants. So based on this, and we know that as the chemical reaction proceeds, it's going to consume new I prime moles of species I, and it's going to create new I double prime moles of species I. And then, so then as the reaction proceeds, we can relate the change of moles to the change of the reaction progress variable times the difference in the stoichiometric coefficients for the products and the reactants. Okay, so we can say that DNI is just equal to D epsilon times nu I double prime minus nu I prime, Okay, and so this here is just the change of moles, the net change of moles of species I between the products and the reactants. Okay, and so now we'll take this definition and substitute it into our equilibrium condition that the sum of d and I g bar I is equal to 0. I'm just going to take this and stuff it in to here, and we have the sum of d epsilon nu I double prime minus nu I prime is times gi bar is equal to 0. Well, this epsilon, or this d epsilon, is constant for all the variables in a given reaction, or for all the species in a given reaction. So we can yank that out and then basically cross that term out. And then what we wind up with is that for a given reaction, the chemical equilibrium condition is that the sum of nu I double prime minus nu I prime times g bar I is equal to 0. Okay. Now, what do we do with this? Well, the equilibrium for, and now we need to start assuming our equation of state. So I'll just recap what this, how we do this for an ideal gas. So for an ideal gas, we have the chemical potential, which is equal to the partial molar Gibbs free energy. That's equal to this term here, which GI naught bar of T. That is called the standard Gibbs free energy. It is the Gibbs free energy at a reference pressure P naught at temperature T, and this P naught is defined to be 1 atmosphere. Okay, and then we add RUT ln PI, which is the partial pressure of species I, and the partial pressure is just the mole fraction of species I times the pressure in the mixture. Okay, and in a lot of tables and books, you can find this basically GI bar. If you can't and you have to put it together, basically G is defined to be H minus TS. So GI naught is equal to HI naught minus T times SI naught. Okay, and then sometimes they will these will be labeled as the standard chemical potentials too. Because again, G, the partial molar Gibbs free energy and chemical potential are the same thing. Okay, so now we're going to take this definition here for an ideal gas, and we're going to put it into, and then sub it into this expression here. And when we do that, it looks like this explodes into a big mess. But I'm going to move the terms with the standard Gibbs free energy to, say, the left-hand side. And this RU log term, I'm going to move it to the right-hand side. And I'm just going to do some simplification. The RU and T are constant for all species, so I can pull that out. And so we have the sum of nu I double prime times the log of pi over p naught minus the sum of nu I prime times the natural log of pi over p naught. This term here, you can just play with some algebra, and this here is just the natural log of the products of the product of pi over p naught raised to the nu I double prime power minus or raised to the power of nu I double prime minus nu I prime. Okay, so we're just playing with some algebra here. And this term here, it's extremely common. We have the sum of nu I double prime gi naught minus the sum of nu I prime gi naught. This term here is so common, it's called delta G naught T, or it's the change of Gibbs free energy between the products and the reactants. And it turns out that even if we use that this term is unchanged, even if we use a real gas equation of state, this term changes, and we're going to go over how that term changes here fairly soon. Okay, and so this term we will define. I'm going to take the exponent of both sides, and I'm going to divide both sides by RUT. And if we do that, we have e to the minus delta G naught over RUT. And that term is called the equilibrium constant Kp. And that's equal to the product of all the partial pressures of species I over the reference pressure raised to the nu I double prime power minus nu I prime. Okay. And I can start playing with some definitions here. So I can have that Kp is equal to this term here. And I can also make the substitution that the partial pressure of species I is equal to the mole fraction of species I times the total pressure in the system. And then I can have that Kp is equal to P over P naught raised to the delta nu. And delta nu is again just the net change of moles across the from between the products and the reactants. And so delta nu is just the sum of nu I double prime minus nu I prime. And then basically I factored out P, and then you wind up with you wind up with the product of all the mole fractions raised to the difference in the stoichiometric coefficients between the products and the reactants. So in your combustion classes, this is actually the version that you used quite a bit to solve chemical equilibrium problems. So you'd find KPT, and you'd find the relationship between the reaction progress variable and Xi, and then use this expression here to solve for the reaction progress variable in terms of the equilibrium constant. When you deal with real gases, which we're going to get to here pretty quick, that term that is not really a practical way to do it anymore. Okay, but I will discuss the effects of Kp and pressure on equilibrium for an ideal gas because a lot of these trends do hold for a real gas. Okay, and so for a constant temperature and pressure process, we know that the equilibrium condition is that Kpt is equal to this expression here, which was sort of derived very sort of very hurriedly on the previous slide, and where the equilibrium constant is e to the minus delta G naught over RUT. So you can see here that if delta G naught is greater than 0, this term here will be smaller than 1. If you are smaller than 1, you know that then the denominator of this product will be, it needs to be larger than the numerator, which basically means that the mole fraction, the net product of the mole fractions for the reactants will be larger than the mole fractions for the products. And so that means if delta G naught is greater than 0, the chemical reaction favors the reactants. If delta G naught is less than 0, the chemical reaction tends to favor the products. And now note, even for a real gas, Kp is only a function of temperature. So if I change pressure or some other variable, but I fix the temperature, Kp does not change. So for instance, if I fix temperature, but I change pressure, what happens then is that basically this term is held constant, and this term here may or may not change it, and then that depends on what delta nu is. Okay. But then what happens if we assume that basically this term here is something other than 0, or I mean something other than 1? What happens if we change the pressure is then that this term changes, but this term does not change. So basically this term here, which involves the equilibrium mole fractions, that has to change in such a way to counteract exactly the change of this pressure term here. So basically what that means is that if you change pressure, the mole fraction term on the right-hand side may have to adjust to enforce the result that Kp is a function of T, and it will be unchanged if temperature is fixed. So if you look at this expression here, if delta nu is greater than 0 and we increase pressure, what happens then is basically this term increases, and since the product of this term and this term have to be constant, if this term increases, this term has to decrease, and if this term decreases, that means we shift the chemical reaction towards the reactants. And if delta nu is negative and we increase the pressure, this term decreases, which means this term here has to increase, or we shift the chemical reaction towards the product side. And if delta nu is equal to 0, at least in the ideal gas limit, there is no effect on chemical equilibrium, period. Okay, and so you can play games like this to examine the effect of changing variables on chemical equilibrium. Okay. Now I will make a note. There are sometimes, if you're doing chemical equilibrium problems and you need GI naught, some books such as Turns' Introduction to Combustion, which is this book right here, will list a property called the Gibbs function of formation, GF I naught of T rather than GI naught of T. And this Gibbs function of formation is defined as the standard Gibbs free energy minus the sum of nu J prime times GJ naught, and where this nu J is the stoichiometric, or is the coefficient of elements that are needed to make the molecule of interest I, but those elements are not the normal elements that you think of. They are elements in their standard state, and where again standard state means the elements in their stable form at standard temperature and pressure. So that is not the H atom, but it is H2, N2, O2, a carbon, graphite, aluminum, etc. Okay, and then by conservation of mass, where we really want this term is finding the delta cap G naught for chemical equilibrium. So you can show using conservation of mass that that delta G naught is defined to be this, but it's also equal to the sum of the nu I double primes for the reactions minus nu I prime times the Gibbs function of formation. Okay, and so I just have a little example down here that if you want to go to and from the Gibbs function of formation to the standard Gibbs free energy, which is right here, we can use this definition here. So here is the nitromethane molecule, and we want to find the Gibbs function of formation for that. It's just the standard Gibbs free energy minus, well, we have one carbon, so that's 1 times the Gibbs free energy of carbon, or the standard Gibbs free energy. And here we have H2, and we have 3 H atoms, and so that would form 1.5 H2 molecules. And so we just subtract off the sort of enough H2 molecules to produce 3 H atoms. That's this here, and similar for nitrogen and similar for oxygen. Okay, so just be aware that that if you use the Gibbs function of formation to compute the absolute Gibbs free energy for a molecule, you will get the wrong number. But typically, we are only interested in delta G. So if you sum them up, you get the exact same number if you summed up the standard Gibbs free energies. Okay, so that's just something to be aware of. Okay. Now we want to apply this to chemical equilibrium for a real gas. So recall that for an ideal gas, and now I'm going to start using the superscript Ig to separate real gas properties from ideal gas properties. So we know that the Gibbs free energy, or the partial molar Gibbs free energy for an ideal gas, is equal to the ideal gas chemical potential, and that was equal to the standard Gibbs free energy, or standard chemical potential at temperature T, plus Ru Ln times the partial pressure of species I divided by P naught, where P naught is the reference pressure, 1 atmosphere. So we would like to use a function that is like this, but also accounts for the real gas effects. And so to do that, we introduce a term called fugacity. I did not name these terms. And so the fugacity for a real gas so using the fugacity, the chemical potential for a real gas is equal to the standard chemical potential, which is the same between an ideal gas and a real gas, plus RUT times the natural logarithm of the fugacity of species I divided by a standard reference fugacity. Okay, and you can think of the fugacity as a partial pressure that accounts for real gas effects. Okay, and so it's a real gas corrected partial pressure, and you can also define a fugacity for liquid solutions, etc. And now for a real gas, you can argue very easily that since P naught is definitely in the ideal gas limit, F naught and P naught are the same. And so we can replace F naught with P naught, and also in the ideal gas limit, the fugacity, just by its verbal definition, the fugacity for species I is equal to the partial pressure of species I. Okay, but using this definition here, we find that the chemical potential for a real gas is equal to the standard chemical potential at temperature T, which again is identical between a ideal gas and a real gas, plus RUT times ln of the fugacity of species I divided by P naught. So the only difference is instead of the partial pressure of species I, we have this sort of goofy fugacity term. Now basically what on earth do we do with this? How do we find that? Well, typically we don't even work with the fugacity. We work with the fugacity coefficient, or at least for real gases, we work with the fugacity coefficient. I think if you're working with solutions and liquids and you're a chemist or chemical engineer, you'll be dealing with the fugacity itself more often. But we deal with real gases, so we're going to define a fugacity coefficient phi I. And phi I is just defined to be Fi over Pi. And so the fugacity of species I is just phi I times Pi. So I'm going to take this and substitute it into our definition of the real gas chemical potential. And we get this expression here. And then I'm going to substitute in that Pi is equal to the mole fraction of species I times P. And so now it looks like I made a huge mess because, I just exchanged not knowing F of I for not knowing phi of I. Okay, so now we need to find that. So let's define an ideal gas pressure, which is needed because if you fix T and V and you compute the pressure, you will get a different number between the real gas and ideal gas equations of state. And using the compressibility factor, we can easily show that P over the ideal gas pressure is this equal to the compressibility factor. Okay, so we know then that the chemical potential in the ideal gas limit for species I is equal to the expression that we've been using. But that's also equal to, if we want to be explicit here, that is equal to the mole fraction of species I times the ideal gas pressure. Okay, and so that's just the pressure evaluated using the ideal gas law. So if I want to find phi, I can define a departure function by just taking the real gas chemical potential and subtracting this ideal gas chemical potential. So performing that and subtracting basically this term from this term, and playing with properties of logs, I get this expression here, and the xi's cancel out, and I wind up with phi I p over pig, and that is just the compressibility factor. So this departure function then is just equal to basically RUT times the natural log of phi I times z. And so now we need to evaluate this and solve for phi I. So we get that the fugacity coefficient is just equal to 1 over the compressibility factor times E times the difference between the chemical potential of species I minus the ideal gas chemical potential for species I over RUT. And so again, this quantity here is a chemical potential departure function, and we can evaluate it the same way that we did any other departure function. Here for these chemical potentials, it is easier to use the sort of second definition, where we basically just take where we integrate from V equals infinity to the volume that we want. And we just take the derivative of our variables here with respect to volume, holding everything else constant, and then integrate that. So you sort of take a derivative and then integrate it, which basically seems kind of silly and stupid, but it's not, because we tend to know the derivatives, we don't know the values themselves. Okay. And so again, we need to find this crazy, and so basically this is just a definition, and on your second homework, you'll be basically using this, you will basically be finding this term here for the BKW equation of state. And so now we need to find the chemical potential and the derivative of that with respect to volume, which you'd think would be an absolute nightmare to deal with, but it turns out there's an extremely useful Maxwell relation that d mu I dv held at constant temperature and composition is equal to minus partial p partial ni held at constant temperature, volume, and all species, or and the number of moles of all other species are held constant. And so this turns a very complicated derivative into a much simpler one using this Maxwell relation here. And so we can find that, then we make the substitution here. We find that our departure function, which can be used to evaluate phi of I, is just this expression here. Okay.
Professor,
and
can I ask a question?
Go ahead.
The chemical potential departure function that we just defined here, we took the partial derivatives with just respect to volume. So are we assuming this is a constant temperature process for this whole thing?
Not for the whole thing, but for the definition of a departure function. So let me get my little notepad out here. See. Okay, so you can see the iPad screen, I think. Okay, so recall that when we defined the departure function, we were integrating in volume. So this would be in infinity and then basically temperature. So we would define a reference state here at Tref. And if we wanted to find the departure function for basically any variable psi, I'll just call this psi1, we would, it's defined to be the difference in psi between psi and the ideal gas limit at temperature T. Okay, and so basically what that integral is doing is we are integrating at constant temperature between basically this point here and that point here. And so this term here is the departure function. Okay, and if you don't know, and since we don't know, we don't know what our variable psi is, but we do know its derivatives. So you can find this length here, or the difference between these 2 points, by just taking the derivative of psi with the derivative of psi with respect to v. So that would be partial psi, partial v. And since it's defined to be at a constant temperature process, it's at constant temperature. And then now we got composition to worry about, but we're assuming that composition is also fixed, except for maybe the one species that we care about. So if we wanted to find that length here, we would basically just integrate that up. Okay, so so does that make sense?
Yeah, I get it now. Thank you.
Yep. Yeah, it's just how it's defined. Okay, and then so yeah, so that's basically in terms of the definitions and stuff. I guess I'll end it for today, but then we will go over a example of how we actually use this for a constant pressure temperature cylinder. And then we're gonna show this process of how we define a Gibbs free energy function and then how we minimize that to find the equilibrium point. So are there any other questions?
Just if we have questions about homework this week, do you want us to email you or were you going to set up office
I
hours?
can set up some office hours. I'll stop recording now.